Now, something that we can talk about when we start dealing with the entire universe is what shape does the universe have? I realize that sounds a little bit weird, but the shape of the universe is related to the total energy density. Hey, that's how much stuff is actually in the universe. Now, if you remember back to general relativity, when we talked about the fabric of space-time as a giant trampoline and we put stuff down on it and these trampoline bends, hey, well, general relativity predicts that the entire universe itself may have an overall shape to it depending on the amount of stuff inside. So if you go back to the idea of the trampoline and you put stuff all over it, then the whole thing might be able to bend in different shapes. Hey, that's kind of this idea that the entire universe itself will be bent in different ways depending on the amount of stuff that is inside of it. Possible shapes. Now in the first case, if the universe has too much stuff in it, if the energy density is too high, then lines that begin as parallel will eventually converge because of the shape of the universe. Now, I know what you're thinking. You've had geometry, and in geometry you learned that if you have two lines that are parallel, they will always remain parallel. And that is true for a flat piece of paper. That is not always true on other shapes. For example, if you imagine a sphere. So, you and a friend are standing on the equator of the Earth, both facing north. Then you begin to walk north. At first, as you're on the equator walking north, you will be walking parallel with each other. However, if you keep going, eventually you're going to bump into each other. And that's because you're not on a flat sheet of paper, you're on a round, spherical Earth. On Earth, all lines that begin as parallel going north from the equator will eventually converge at the North Pole. So, this shape of the universe, where if we have too much stuff, parallel lines converge, this is known as spherical space, sometimes called a closed universe. So, in a closed or spherical universe, lines that begin as parallel will eventually converge. Another possibility is if there's not enough stuff in the universe, if the energy density is too low. In that case, we have the opposite curvature. So instead of parallel lines coming together, we have parallel lines that eventually separate. They diverge. The sort of shape that has parallel lines diverging is a hyperboloid, kind of this weird saddle shape you see here. So this is referred to as hyperbolic or open space. In a hyperbolic universe, lines that begin as parallel will eventually diverge. Now we have one last possibility. If the energy density is exactly right, this is what we refer to as the critical density. If the universe has exactly the critical density, then lines that begin parallel will always remain parallel, just like on a flat sheet of paper. So this is known as a critical or a flat universe. Now, just to summarize, if the energy density is too great, then we have a spherical universe. If the energy density is exactly right, notice that is an equal sign. If it's exactly right, then we have flat space or a flat universe. And if there's not enough stuff, if the energy density is too low, then we have hyperbolic space. Now looking at these, what is the likelihood of flat? Okay, to have a flat universe, we have to have the exact right amount of stuff. Probably not going to happen. All right, well, we can actually test to figure out the shape of our universe. Specifically, we can look at the oldest light that it is possible for us to see, which is known as the cosmic microwave background, or CMB. We'll talk more about the formation of the cosmic microwave background later on when we talk about the Big Bang, but for right now you can simply think of it as the oldest light that has been left over from the Big Bang. This is the oldest light it is possible for us to see. Well, as we look at the cosmic microwave background, we see that there are hot spots and cool spots. So these red regions are hot and the blue regions are relatively cool. The hotter regions correspond to slightly higher density, and the cooler regions correspond to a lower density. This is actually showing us the seeds for the large-scale structure. The hot regions are going to collapse and will form into galaxy clusters. The blue, cool regions will have material swept out, and those are going to form into voids. So what we can do is we can look at the scale of galaxy clusters. So we have galaxy clusters here in the local universe. We know how big they are. And what that means is we know how big the hotspots needed to be at the beginning of the universe for them to collapse into the size of the galaxy clusters we see today, which means we know how big those hotspots in the early universe on the cosmic microwave background needed to be. So we can compare the scale of these hotspots. Okay, are they too big, just right, or too small? If the hotspots are too big, then that means that we've had a magnifying effect. In other words, the light from these hotspots has converged, creating a magnifying effect. So if the hotspots are too large, we live in a spherical universe. If the hotspots are the right size for what we expect to form galaxy clusters today, that means that the light has traveled on perfectly straight lines. In other words, parallel lines would have remained parallel, and therefore we must live in a flat universe. If the hotspots are too small, then the light has actually had a minimizing effect, meaning that parallel lines have diverged, and in which case we would live in a hyperbolic universe. So if they're too big, we live in a spherical universe. If they're just right, we live in a flat. And if they're too small, we live in a hyperbolic universe. Well, when we've actually gone out and we've done these studies, the hotspots on the cosmic microwave background are the exact size that we expect, meaning the universe must be flat. Now, that sounds pretty awesome because it means that the geometry that you learned on a flat sheet of paper happens to work with the entire universe, which is nice. However, this actually leads to a couple of problems. One is the likelihood of a flat universe was essentially not. That's something we're going to have to address, and we'll address it next time. However, the other problem is that for the universe to be flat, we have to have the critical density, meaning we know exactly how much stuff we have to have in the universe for it to be flat. But when we go out and we add up all the stuff that we know about in the universe, so this is all matter, that includes normal matter as well as dark matter, and we add up all the light and all the energy and everything, we end up with 32% of what's necessary. Okay, that means that 68% of the universe is actually missing. Okay, so this 68% of the energy density of the universe, we can say a couple of things about it. One, it doesn't give off light. If it was 68% of the universe and it gave off light, we would see it. So it does not give off light. Also, it does not have a gravitational influence. If you remember, the reason we know about dark matter is because of its gravitational influence on the stuff we can actually see. And if there was 68% of everything that had a strong gravitational influence, again, we would absolutely see it. So we know it doesn't have a gravitational influence like dark matter, and it does not give off light or interact with light like normal matter. So that's where we are. Now, whatever this stuff is, to help ourselves feel better about it, we give it a name. We refer to it as dark energy. Now, because of the amount of dark energy in the universe, whatever dark energy is doing is going to control the eventual fate of the universe. We say that the universe is dark energy dominated. As we figure out what dark energy does, this will then tell us how the universe is going to continue to age and how it will eventually end.